Hi, David Vizard here, and you're watching PowerTec 10. In this episode of PowerTec 10, we're going to deal with the idiosyncrasies, and I think that's the best word to describe it, of the rocker arms we use on our pushrod engines. Now, I can tell you right at the beginning, this is a lot more complicated than you may ever think. I'm hoping that I don't leave anything out, and we may have to run to two episodes to cover all this. First, let me give you a few thoughts on some things that you might not have seen before. Here's a degree wheel, very important, right? And there's something special about this degree wheel. It has two scales on. Be interested if anyone can guess what that's for and how it works. Here's another statement I want to make. Cam testing, which is done without an adjustable timing sprocket, like the one I've got here, is not going to be a valid test. Here we've got an adjustable sprocket from Comp Cams. This features not only an adjustable inner body to the timing gear, and here's the marks here for the advance and retard. I think you can go up to about 8 degrees either way, right? Also has this needle roller race here, thrust bearing. Now this is used in conjunction with a split cover like this. I like these split covers because you can get the seal there right with your silicone sealer. It doesn't leak, right? And the other thing is it looks slick. Let's take a look at these liner rockers here, right? Basically they're lined up in the order of cost. But the thing is we're going to investigate the geometric properties of these rockers because they vary hugely, and that I don't use that word in vain. So let's start the ball rolling here. Principally this episode, or possibly two, depending how long it goes, is about rocker ratios. Now it may look very simple. You either use a 1.5 or a 1.6 or 1.65, and so it goes on. However, two rockers supposedly of the same ratio do not necessarily deliver the same power. I'll give you an example. While I was lecturing at the university in Swansea in England, well, Wales actually to be more precise, I was also having Terry Walters run some dyno tests for me on the big block that we were doing for GM, the update of the 572 street motor. Anyway, the thing was we tested two sets of 1.8 rockers. They lifted the valves within 5 thousandths. Each one was optimized. Do you think there was any difference between a 1.8 and a 1.8 with only 5 thousandths difference in the lift? I'll let you know at the end of this video. Okay, let's get down to this rocker ratio business. Here's a chart which I hope explains the basics of how rocker ratios can change and how what's stamped on them may not be that accurate. So that you can see how the rocker ratio may vary, I've done this diagram here. Crude, but it should illustrate the point. Here is our valve stem. Here is our pushrod. Now, I've got one line drawn straight through the fulcrum here, right? And this, if that was to push up like this, and that pushed down like that, the rocker ratio would be exactly 1.5, right? But it doesn't push up and down like that. It pushes at an angle like this. You can see that the push rod is operating at a distance from the fulcrum equal to that. Right? Now you will see that this distance is less than this distance. You see we've got a right angle triangle here, and this is the hypotenuse. Now then, most rockers are designed, well, in fact any rocker worth its weight is designed such that the sweep of the end over there, change in direction, is the least, and they do that by dropping this down. Now this length here, this hypotenuse here, is exactly the same as that. When the push rod pushes up on that, the radius that it's operating on from the fulcrum is only this much. So you can see that there's three possible scenarios here. Rocker ratio 1, push, push. 2, operating at that ratio, push, push. And 3, this one. Now you can see that altering your push rod length here alters the angle at which this comes in. And so the length of the push rod can also alter the ratio. Now as the rocker gets up in lift, so this distance, the sweep here, is going to go like that. So the radius from the tip here, which will be up here, is now bigger, right? And it's increased more percentage-wise than the radius of sweep of this. So as the rocker increased in lift, so its ratio dropped off. Now this is a drawing of how the mechanism works, right? A rocker designer can move these around to get a wide variety of angles at the end there. What I'm demonstrating here is a typical aftermarket rocker for a typical V8 engine, a la big block Chevy, big block Ford, small blocks. So you can see that when the ratio is quoted, it's only a guesstimate at best. What happens is they'll design it with the push rod at somewhere near where it should be, and then stamp on it what ratio that would deliver under those conditions. Well, it's a chance in 100 that you'll have those conditions. So the lesson to be learned here is the ratio stamped on the rocker is not necessarily the real ratio. Now let's get down to some details on that. Okay, now we've covered the subject of geometry, well, loosely covered it. Let's talk about why these ratios are important. Let us not forget the fact that every 2-valve engine compared with a 4-valve engine is undervalved. This being the case, it's very important, especially if we have an exhaust system which is working well and scavenging the chamber, that we open the valve, the intake valve, as fast as possible. Now, the more undervalved an engine is, the more we need to do that. The big block Chevy is a prime example of an engine that is undervalved. So, in theory, opening the intake valve faster should make more power. Now, there's a couple of provisos that go along with that, but we'll get to those. Now, let's talk about a stroker motor. Let's say that the rocker ratio was adequate for, say, a 350, and you put a stroker crank in there and make it a 383. Well, for it to be adequate for the 383, it needs to open the valve in basic terms about as much faster as the displacement increase. So if we had say an 8% increase in displacement, we need the valve to be 8% further open at every point in the lift range. Again, there's a few provisos which go with that. So here's a situation. In theory, we need to have rockers which lift fast off the seat and have a good final ratio, but need not be that, how should we say, aggressive or that big. Having said that, I'm going to give you an example where that might defy that statement. What we have here is one of my favorite rockers when I'm doing big block builds. It's a PRW rocker. Now, a lot of you won't have heard of that company, but they make some nice stuff. A lot of it goes to the trade. A lot of you who are professional engine builders will probably be using their parts. And this is their top of the line 1.8 rocker for a big block. Now that's, according to that 1.8, it's a 0.1 of a ratio up on a stock rocker. Well, the stock rocker has a lift off the seat of about I'm trying to remember, it's all in my big block book. It's about 1.68. This rocker coming off the seat is 1.96, and at peak lift it's typically around 1.92. Now, if there's ever an engine which needed fast off the seat and high lift, it's the big block Chevrolet. So, are these worth power? You bet they are. Now, toward the end of the video, and it looks like I might get to it, I'm going to give you an example of how much horsepower a fast off the seat rocker can practically generate. And I'm also going to show, had this been tested by a magazine, it would have almost probably shot down my theory about having it fast off the seat. You'll see what I mean toward the end of the video. Anyway, is there a downside to a fast off the seat rocker? Yes, there is. You need to use a better quality cam. You can't be using one of these cams out of a cheap catalog. I remember checking a PAW cam. They're not in business anymore. It doesn't surprise me. But one of their cams turned out to be about a third or a fourth generation copy of a crane cam. There's a certain characteristic which hadn't got blended out by continual regrinds. But the bottom line was this: the dynamics on it were terrible, right? It floated the valve train much sooner because of this, and it did not like having high lift rockers on it because that just exaggerated the situation. So bottom line here is, if you're going to buy a cam, do yourself a favor and buy one from a reliable source. If you get one that's got a lot of jerk and other third and fourth order effect dynamic problems, that's going to result in reduced power and a greater chance of broken valve springs. Also, high lift rockers won't be liked on that cam. Now, let's look at some typical some typical ratios of big block cams. If you go through my big block book, you'll find that they range from anywhere to just below the claimed ratio to well above it, like this PRW one. There's several main brands which do lift the valves off the seat faster because of the higher ratio they have initially. It's all in the book. PRW is not the only one, it just happens to be the one that has the most acceleration off the seat. Okay, I think we've got time to get to it. I'm going to do the story of the 1.8 rocker versus the 1.8. So hold your horses, because here we go. Well, let me start by setting the scene here. This would have been probably about 5 or 6 years back now, and I got this job from GM to look into some updates for the 620 horsepower 572 street big block. That's the one that runs on 87 octane fuel and has 4:1 compression. Well, we went ahead with this, and of course I have a busy schedule, or schedule, whichever the word is. I guess depends on which side of the Atlantic. The thing is we wanted to deliver the results of GM as quickly as possible. So whilst I was away lecturing in England, Terry Walters, we did all the testing up at his shop, carried on and did some tests without me there. Didn't need me. We'd outlined what we were going to do, and that's what he was going to do. We were going to check some rockers, and their initial ratio off the seat was about 1.76, and the rockers we were going to use were some fast off the seat crane rockers, which were about 1.88 off the seat, so nearly 1.9, and that was the deal. Now, at the time this test was going on, I was doing a seminar in Swansea University. So we put the results that came in from Terry on a transatlantic call over a speaker so that they could be involved in the tests at the same time I was. Anyway, dynoed the base engine. Now, I can't remember the numbers exactly, the actual base numbers exactly, but they're in my big block book. So, but I can remember the gains involved, and approximately the gains or losses at intermediate stages. Well, the first set of rockers was the regular ratio off the seat, and the engine was really dialed in on these rockers because we'd used those for most of the testing to date. The engine had an adjustable belt drive, so we could always optimize cam timing. We'd already put in a cam that I spec'd out, which incidentally picked up 12 horsepower and 80 foot-pounds over the factory cam, right, which was spec'd out by some genius at a cam company. I don't know which one, but it wasn't anywhere near where it should have been. Anyway, from there we went to checking the lash, and again adjusting the timing, checking the lash, and dialing the lash in on the rockers as close as possible exactly what the engine wanted. Again, mixture and timing were just right on, and it got to the stage where anything we did to that engine, right, the power dropped. So we were pretty confident we'd optimized everything out. At this point, Terry calls up and says the engine's ready for a change in rockers. So I said, go ahead, change the rockers, and it's a solid cam. So I said, I want you to make sure you lash the rockers exactly as they were before. I don't want any changes other than the rocker ratio. So that was done, and about 50 minutes later I get another call, and sure enough, it was just as I expected. The engine had dropped 12 horsepower. Now, it was making close to 800 at the time, so 12 horsepower, you wouldn't really notice it, but on a dyno you can see it. That's why we have dynos. Right, now, I'm going to make a bet. Had a magazine tested these rockers and was going to try and prove or disprove my theory about fast off the seat, they would have said, aha, back-to-back tests, we changed nothing but the rockers, and look, Vizard was wrong. Well, I get that a lot. But here's the thing. When you change the rockers for a different ratio off the seat, You also change, and if you're setting the lash exactly the same, you change the point at which the roller picks up the cam profile from the base circle. So in effect, what we had done was we had reduced the lash seen at the lifter cam interface. What was needed here was to increase the lash to compensate for the higher ratio rocker. And it turned out that that compensation was about 2 thou. So that was done. That was the next move. Oh, we just put the rockers on the intake. I forgot to say that. We just put the rockers on the intake. It's not a big deal on the exhaust. Anyway, about 30 minutes later, I get a call from Terry. Yes, the motor is now up 2 horsepower. Well, that's not a lot of horsepower for a big change in rocker ratios. And I said, okay, because we've only got the rockers on the intake, the cam looks like it's advanced, right? What we've done is we've increased the intake opening area of the advance envelope, but not the exhaust. I said, now we've got a cam which for what we've got is too far advanced. Now, I've done tests like this numerous times when I've been testing cams, so I knew what to expect. And I said to Terry, I said, retard the cam by 3 degrees. Right? Okay. About 20 minutes later, he calls me up. We've done that. Now, remember, there's a class of people listening. Okay, Terry, tell us what the results were. We were up 18 horsepower. So, this is my point here. When you are fooling around with rocker ratios, unless you look at the lash and the timing, you cannot just do a back-to-back rocker ratio by take this one off, put this one on. Doesn't work. The domino effect once again comes into play. Thank you.